Hey everyone! Welcome back to Free Lectures for All. Today we're diving into an important concept in databases: database normalization. If you've ever wondered how we keep data organized, avoid redundancy, and maintain consistency in databases, normalization is the key. Let's break it down step by step. Imagine you're building a database for a college. You create a table like this. This table contains information about departments in some college. The relation name is department, and it has the attributes: roll number, name, course, instructor, and instructor phone. Looks fine, right? But wait. Do you see the problem? Dr. Mata's phone number is repeated. If his phone number changes, we need to update it everywhere. And if we forget, we'll end up with inconsistent data. Similarly, if the course name changes, we must update all the corresponding cells. This type of issue in a data table is called an update anomaly. Another problem we face with an unnormalized data table is the insert anomaly. In this case, we cannot add a new course unless at least one student joins it. The next problem is the delete anomaly. If the last student enrolled in DBMS is deleted, the instructor's information is also lost. All these problems can be solved using a process called database normalization. This is where database normalization comes in. Normalization is the process of organizing data into multiple related tables in such a way that 1. Redundancy is minimized. 2. Data integrity is maintained. 3. Updating, inserting, and deleting become easier and safer. Normalization is done in steps called normal forms. As you go from a lower-order normal form to a higher-order normal form, your data tables become better and better at handling redundancy, update anomalies, insert anomalies, and delete anomalies. Let's quickly go through them. We start with first normal form. If a data table is given, the first thing we check is whether it satisfies the conditions of a relation is in 1NF if all attributes are atomic. Each record is unique. Let's see an example of a table which is not in first normal form. Imagine we have a data table for some department of a college, like this. This table contains information about departments. The relation name is department info, and it has the attributes: roll number, name, course, student phone, credit, and lectures. In this table, Raj has multiple values in the course attribute DBMS and OS. So the value of course is not atomic. Similarly, the attributes credit and lectures also have multiple values. The same case exists with Priyansh. Therefore, we can say this table is not in first normal form. To convert it into first normal form, we must make sure that the values of each attribute are atomic. Here, we can achieve this by splitting Raj's tuple into two tuples. One with course equals DBMS, credit equals 6, and lectures equals 6. Another with course equals operating systems, credit equals 4, and lectures equals 5. Now every attribute has a single value, and the table is in first normal form. We have converted our table into first normal form. Now, let's check if it is in second normal form or not. A data table is in second normal form if it satisfies two conditions. It must already be in 1NF. There should be no partial dependency. To understand the second condition, we first need to understand what partial dependency means. But before that, let me clarify some terminology. Candidate key. A candidate key is a set of attributes that can uniquely determine all other attributes in a relation. In our example table, the set of attributes roll number, course can be considered a candidate key. Other combinations like roll number, credit could also be candidate keys. Out of these, we can choose any one as the primary key. Let's say we choose the combination roll number and course as our primary key. Now, attributes can be divided into two categories. Prime attributes, attributes that are part of the primary key. Non-prime attributes, attributes that are not part of the primary key. In our example, the prime attributes are roll no and course, and the non-prime attributes are name, student phone, credit, and lectures. Now let's define partial dependency. Partial dependency means that a non-prime attribute depends only on part of a composite primary key, not the entire key. In our example table, the attribute student phone, which is non-prime, depends only on roll no from the composite key roll no, course, not on the whole key. Similarly, the attribute credit depends only on course, not on the entire composite key roll no, course. Because these partial dependencies exist, our table is not in second normal form. Host. To convert this table into the second normal form, we must remove partial dependencies by dividing the table into smaller relations, where each non-prime attribute fully depends on the whole primary key.